So this is the analysis part for the control systems. We have let me summarize this part. We have talked the way to express a fractional transfer function in Matlab, and we can easily find the interconnections of fractional transfer functions easily by using multiplications, plus, or feedback functions. We can easily find the overall model. And then we talk about the analysis of linear systems. And then we talk about the analysis of nonlinear systems by simulation method, where a block diagram, where a fractional differentiator block is defined. We can use the block for modeling complicated fractional nonlinear systems. And now we come to the point: how can we design controllers? Integer order controllers or fractional order controllers. Here I tried several examples for integer order controllers and fractional order controllers. So I will give something in detail for those controllers. The first thing I want to demonstrate is the PID controller graphical user interface. By with the use of the interface, we can design controllers, integer order PID controller for standard FOBDD model. And also we can use the PID controller design method for other types of model where the model can be approximated by this kind of Planck model. And the approximation can be performed using time domain method, frequency domain method, or suboptimal optimization method. And we can, for a given transfer function, we can first approximate it to this form where we can find K, E, and L. And then using the tuning rules, and the one I will recommend is the one listed in the book, which is called the Handbook of PID Tuning Rules. I think it is published by Imperial College a few years ago. Ireland people think. So I've implemented hundreds of tuning rules in the interface, and you can choose different tuning rules and compare the tuning results. So there is a graphical user interface. Let's try a prompt model like this. If you want to design a PID controller, you can type PID tuner, the program name, I call it is PID tuner. And in the PID tuner, you are required to input the Planck model. If you click this one, and you can specify the numerator and denominator of the Planck model, and also the delay time. For the model I used, I think it is 1 plus S plus 1 cubed, and then the delay is minus S. The delay is 1. So for this Planck model, we can express it here 1, 3, 3, 1. This is the denominator, and the delay time is 1. So this is a description to the actual Planck model I want to try. And you have entered the Planck model already. And then the next thing we need to do is to get the FOPDT model, where we have to get the K, L, and T model for the plants. We can use approximation method. We can use suboptimal optimization, model reduction, and then click this button. So you can have K, L. So where is this question? Where is T? I think the display might have problems. And now we can select the the controller type, PI controller, PID controller, and modified PID controller. Let's try PID controller and select a tuning rule from here. For instance, we want to get servo tuning, and there will be a list of tuning algorithms given in this part, so we can select one of them. And then we can click this icon to design a controller. And this is the controller design. And then we can draw the closed loop step response of the system. So this is the closed loop step response of the system. We can change the range in time domain. For instance, we can use 20. And we can hold the result. And we can change another tuning rule from the list. And design controller again. This is the controller. And then we can perform closed loop simulation. And in this way, you can compare different tuning rules and see which one gives the good result. So this is the user interface you can download from the web page of the course.
Just one question. Can you always get the KLMT?
KLT, I think there should be a T, but I'm not quite sure why the T is not displayed.
No, I mean, can you always get
No.
it?
If the step response of the plant model is something like this, or even if there are oscillations, you can get KLT. If it is something like this, then you cannot design controller using this algorithm. You have to use something like KS, this kind of plant. But you have to search for the control. You have to search for design tuning rules. I think in the handbook, another kind of tuning rules. In this program, I only implemented the plant model, which can be fitted like this. Even if there are oscillations or something like this, since PID controller has certain robustness, we can still use it. However, if the system cannot be approximated well with this kind of model, this program cannot be used. So there are limitations in the program. I only implemented in part of the PID tuning handbook. I think there are around 100 tuning algorithms implemented in the program. You can download the program and use it and try it yourself. I think it's pretty easy to use. You can select different kind of controllers and different kind of purposes for servo tuning, robust tuning, and something like that. And then you can, in each group, you can select one of the tuning algorithms. So this is one example we can use. The other one, I think I've already discussed it in the other lecture. Here I only repeat some of the useful results. So how can we get an optimal controller? By saying optimal, we have to say what is the objective function we must choose. And in control literatures, normally we see that there are LQ, linear quadratic. For instance, there are linear quadratic controller, or even linear quadratic regulators. So what are the differences? If you go back to control course or linear system course, you may find that to get an optimal controller, since the computer and software was not well developed at that time, if we date back to 30, but 40 years ago, so they introduced a criterion like this to say if this is optimal, then we can get a certain kind of optimal controller.